guess I should start just with some story, and then hopefully the rest of the people will arrive. So the point of this business with finite-dimensional algebras is essentially that, well, we're interested in coverings. Like, for instance, let me draw you the picture. You have a circle which covers a circle. Map goes T goes to double T. This is an example of covering. Another example is when you have a sphere, Sn or S2, for instance, covers, again, 2 to 1, projective space, Rp, P2. Rp2 is a space of lines passing through 0. And if you have a sphere, in fact, this is the same map for Rp1. If you have a sphere, you can, every point on a sphere gives you a line, but there is another point. So if you glue these 2 points, you obtain Rp2. So formally, if you know topology, a covering is a map such that for each point in the image, there is a open for each x inside. So you have n to m. For each x inside m, there exists an open neighborhood containing this x, such that f minus 1 of u mapped to u is just several copies of u are mapped to u, is several copies of u mapped to u. Like that. If you, I mean, globally it's a circle, this is a circle, but locally for each point there is an open neighborhood such that its preimage is 2 copies of this neighborhood. And if you have the same, you can check this for a sphere and for other examples of coverings. So important thing about coverings is that if you have a complex analytic map, this is actually how Riemann invented the notion of a manifold. If you have a complex analytic map, F, like let's consider polynomial map F from CP1, well, for complex to complex numbers. Of course, it might have some critical values. But outside of these critical values, you remove the critical set S here. You remove the critical set F minus 1 of S. Then it is again, if you remove this, remove like this, then it is a covering. For simple reason that every polynomial has precisely n roots if its degree is n, and these roots, as long as they're distinct, smoothly depend on the coefficients of the polynomial. Okay, and this is the geometric situation you have to work with in algebraic geometry. For instance, if you are interested in finite maps. But there is a way of doing that, and it is called Galois theory. In fact, Galois theory can be constructed for coverings. There is a version of Galois theory for coverings, and essentially, if you look at this Riemann picture with covering from then just automorphisms of C, which are compatible with F, is precisely the Galois theory of the corresponding polynomial. Which I'm not going to define. Well, we shall discuss that, but I need only a small part of it. Okay, so there is this basics which we have already done, extensions. if you have a field and a subfield. It's convenient to denote this. This is what people do in number theory, in Goulart theory. This is extension. So you have bigger field, a smaller field, and bigger field is a vector space over the smaller field, and it's finite if k big is finitely dimensional over k small. This is something we have done. Then if you have an element of this finite extension, it's called algebraic number or algebraic element in the big K. If K, all elements are algebraic, it's called algebraic extension. Sum of product of algebraic is algebraic, and also division. Yeah, this is something we have done. Do you have any questions about that? There's an important notion of algebraic closed field, field which has no non-trivial algebraic extensions. And C is algebraically closed. We have discussed that at some point. Do you know that every field, for each field K, there exists algebraic closure? Algebraic closed K bar, algebraic over K small, and it is unique up to isomorphism. Do you know this? At some point, unfortunately, I would have to use this. Well, if you like, I can actually prove this. The proof is sort of complicated, and there are several ways of doing it, and they're all, well, we can discuss in the end of today's lecture what we want to do with Goulart theory. So existence of this K bar is part of Goulart theory, and it's not very hard. At least for characteristic 0, it's not very hard. For characteristic 0, it's not very hard because at least if your field is not very big, you can embed it to C and then take smaller subfield in C which contains this and is algebraic. Anyway, you can just take C as algebraic closure in most cases. Now, today I will speak of K algebras and K rings. The problem, of course, the whole course we always consider rings with unity. Today, it's not always so, because we're interested in such thing as a direct sum. So if you have K1 and K2, two fields, there is a way of making this into an algebra. Just you take x plus y, and you multiply it to x prime plus y prime, and you obtain x prime or y prime. This is a very natural operation. You just term-wise add them, term-wise multiply them. It's a very natural operation. It's really easy to see that it makes it an algebra, but this is sort of subalgebras. But they're not. They have unity, but the map is not compatible with unity. In fact, all these algebras we shall discuss today, they all have unity, but the unity is different. And because usually we consider such algebraic objects. So I would use algebras when so in algebraic geometry, unity is mapped to unity, but not here. Well, I'm not entirely correct, so it's better to forget. Anyway, K algebra is just a ring which contains K as a sub-ring. Do you have any questions about this? So the algebra and ring is pretty much the same. But, OK. Now the minimal polynomial is something you probably have seen in linear algebra. And in fact, if you think about that, if you have A in an endomorphism, endomorphism over K of vector space, V finitely dimensional vector space over K, then the minimal polynomial. Have you seen that in linear algebra? Of A is the minimal degree polynomial P of t inside the K of t, such that P of A is 0 in endomorphisms of V. Okay, now we define the same way for any K algebra. If you have A is K algebra, in fact, you can think of K algebra as sitting in its own endomorphisms. And then you define minimal polynomial the same way. Min poly of, say, x of x is minimal degree polynomial. It's better to, just for definiteness, to ask them being monic, being the leading coefficient 1, but it doesn't matter. Minimal degree polynomial P of t such that P of x is 0. Okay, the important thing about minimal polynomials is that if you know minimal polynomial, you know your algebra. At least you know the algebra generated by x. So claim, suppose that x inside A and generates A. And then you write, and so now I'm assuming that A has unity. Not sure we need that, but let's assume that for simplicity. And P of t is minimal polynomial. X, then A is K of t, the polynomial ring quotient by P, by the ideal generated by P. Let's prove that. So everybody knows this already? Who knows this? Okay, most people know, so I will be won't take much time. So proof. Suppose you have Q of t, Q of x is equal 0. Then you use a Euclidean algorithm. Using Euclidean we obtain R of x, biggest, greatest common divisor of P and Q, such, and R is P times, say, A plus Q times B, where A and B are polynomials. You just use Euclidean algorithm and you express the greatest common divisor as a linear combination, but then since these both guys vanish on x, R of x is 0, and then degree of R is the same as degree of P, because degree of P is minimal. Then they're proportional. So this means that the ideal P is ideal of all polynomials Q, such that Q of x is equal 0. And of course, you have a surjective map, by definition, from polynomials to A, mapping T to A, to X, this map. This is surjective because X generates A, and the kernel of this map is precisely this ideal, which proves this claim. Questions, comments? Since I assume you know, most of you know this, I'm not spending time on it, but maybe you still have questions. Okay, so factorial rings are rings with where you have prime decomposition which is unique. So definition, factorial ring. We have that in a handout, more precise statement. Ring is a ring with unique prime decomposition. It's slightly weaker than principal ideal domain. So every principal ideal domain, like Z or polynomials, principal ideal means that all ideals are principal, generated by one element. So this is slightly weaker. For instance, this is something we shall probably use at some point. There is Gauss' lemma, which says that polynomial ring of any degree of any dimension is factorial, but of course it's not principal ideal domain. This is something we discussed. Okay, but since we have Euclidean algorithm, this simple argument implies that remark, polynomial ring K of T is factorial, because it's principal ideal domain. So every two elements have a canonical greatest common divisor, and this gives you a prime decomposition for any element. Okay, so definition, polynomial P of T is irreducible if it is prime in that sense. Reducible if P of T is not a product of P prime times P double prime, well, P1 times P2, where degree of P1, degree of P2 is less than degree of P. This means that you can decompose it onto polynomials of smaller degree. And then this is something you know about prime numbers, but the proof is the same for polynomials. So is it theorem or proposition? Proposition. So P of T inside the polynomial ring is irreducible if and only if polynomials quotient by the ideal generated by P has no zero divisors. So who knows this already? Please raise a hand. Not everybody, sorry. So let me explain how it is done. It's not hard. So proof. First, if you have such a decomposition, if P not irreducible, then you have P1 times P2 equal to P, but this is equal to 0 mod P. And of course, since P sufficiently big degree, then for polynomials of smaller degree, they are embedded to this quotient. So these are non-zero elements. So if it is non-reducible, then it is zero divisors. Divisors. Conversely, if P, now we want, if P is irreducible, and then it is prime. And if you have P1 times P2 equal to P times Q, then P1 or P2 is divisible by P. This is because P is prime and it has to enter P1 or P2 in prime decomposition. So this is where you use factoriality. Okay. But this is the same as for finite fields. We know that if P is prime integer number, then the quotient Z by P is a field, and the proof is the same. Of course, I didn't tell you that it is a field. I just told you that it is has no zero divisors, but in fact, this is the same. I hope we have it on the next slide. No, we don't, but it was some previous slide I just forgot to tell you. So if you have K, some algebra A, no zero divisors, so it's claim, we had it, no zero divisors, and A is finitely dimensional over K, and then A is a field, and proof. Okay, we have an operation of multiplication Lx of A is just multiplication, so it's is equal to xa. Kernel of Lx is equal to 0 because no zero divisors. But then it's fine dimensional space. A is fine dimensional. Then Lx is, it's not only injective but surjective because it's in the morphism of a fine dimensional space. Surjective. And then there exists y such that Lx of y is equal 1. This gives xy is equal 1, so x is invertible. Okay, so we discovered how to obtain fields from polynomials. So fields are more or less the same as irreducible polynomials. So let me state this precisely. So definition. So element x inside K. So suppose that K over K small is extension. And the element called primitive, if x generates K big over K small, generates in a multiplicative sense. X, x squared, x cubed, and so on. And then in that case, in this case, K big is a polynomial ring quotient by minimal polynomial. This is called primitive extension. K big over K small. So it contains a primitive element. And then there is a claim that, which is trivial, that every finite extension can be obtained by adding So you add x. If x is primitive, you are done. If it's not, you just add it and you obtain a bigger field. You add one more. And every time the dimension increases, so at some point, since it's finite, you will end up with being your big K. In fact, I will prove today, if I have time, that in characteristic 0, every extension is primitive. So you always have this. In fact, the general element is primitive. Have questions, comments? No? Okay. So today I'm mostly interested in fine-dimensional algebras over a field. This is essentially algebraic varieties of dimension, degree 0. But not over C over any K. So definition, commutative, associative, K algebra, which is fine-dimensional over K, could be without no unity assumption, is called Artinian. So usually we have unity, but it is somewhere. It's not, when we speak categorically, we are interested in morphisms of such objects. They typically don't preserve the unity. So now it's called semi-simple. So it's A. A is called semi-simple if A has non-nilpotence. Non-zero. And I will prove, not now, but in a couple of slides, I will prove the following important theorem, that any semi-simple Artinian algebra is direct sum of fields. So theorem, every semi-simple. So we discussed what is direct sum of rings. In fact, you just take direct sum and you multiply them term by term. This is something I have already written on the blackboard. Every semi-simple Artinian algebra, K algebra, is direct sum of fields. And this decomposition, is unique. Is unique up to permutation, of course. Is unique up to permutation. Okay, so this is an important result, which I'm going to prove slightly later. Do you have any questions so far?
Professor, how can I obtain that sequence of primitive extensions which give in the previous slide?
Yeah.
How can I obtain the sequence of intermediate extensions?
You take any element which doesn't belong to small k. Yeah. You generate a subring, and since it's fine dimensional, it has to be a field. Okay. If it is everything, you are done. Suppose not. Let's take another element and add it. You obtain a bigger field. Bigger, 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 but every time dimension increases, but dimension is finite, so it has to stop. Okay. Okay, good. Thank you. More questions, comments? Okay. So how we describe these subfields? Well, they have their own units. How you know these units? They are elements which are squared to themselves. So definition, element E inside A called idempotent if E squared is equal to E. So we have obvious examples, 0 and 1 are examples of idempotence. But there are more. If it is a direct sum of fields, obviously you have more idempotence, just units in each of these subfields gives you an idempotent. So the important thing that every there's a slight error here. Product of two idempotents is idempotent, and there's couple of easy remarks. E prime idempotent, then E prime is also idempotent. And also if E is idempotent, then 1 minus E also, because you take 1 minus E squared, you obtain 1 minus 2E plus E squared, but this is same as 1 minus E because E squared is E. Have you heard about Boolean algebras? The funny thing about idempotence, they form Boolean algebra. What is Boolean algebra? It's a set where you have logical operations. You have x, y, you have x conjunction with y, it's E and you have x disjunction with y, which is OR. And you have negation. I'm not going to prove this. This is an exercise, but it is really, it was helpful for me at least to understand that now you have operation on idempotence. Operations on idempotence. Xy goes to xy. X goes to 1 minus x. This is conjunction. This is negation. And then you have disjunction, the OR operation, which is xy goes to 1 minus x times 1 minus y and 1 minus this. So these are two idempotents. The product idempotent, 1 minus idempotent is idempotent. And you can check that all relations in Boolean algebra are satisfied. So this is how you can somehow work with idempotents as if they're statements in logic. I'm not going to use this. What I'm going to use is the following, that if you have, if you have A, B idempotents, A plus B is equal 1, this means that A is E and B is 1 minus E. Then you have every element x is AX plus BX. Yeah, and AB is 0. AB is 0 here because if you multiply, you obtain 0. And then this is a subalgebra. This is a subalgebra. And if you multiply these two guys, you obtain 0. This means that A is direct sum A plus B. This is what you can call them orthogonal unipotent. So this is orthogonal unipotence. So one is negation of another. And if you have such decomposition, this gives you a decomposition of your algebra, in particular, an algebra which has unipotence is automatically direct sum of two subalgebras. Questions, comments? Should I go on? Good. Okay, I'm moving towards this theorem, but I will start with a simpler result, that any algebra, well, this theorem is wrong. It should be non-zero multiplication. I mean, you can have trivial case where just product of everything is zero. I forgot to mention this. Then this proof obviously fails, and you can see when. Okay, theorem. A Artinian product non-zero product. Then A contains idempotent. Proof. There is a more general notion of Artinian, even Artinian categories. So Noetherian algebra, Noetherian ring is a ring where you don't have increasing ideal chains. And a category is category when you don't have increasing moduli, like increasing submoduli, or sub-objects. And the same Artinian category is opposite. Is a category when you don't have decreasing subset, decreasing chain of ideals. So Artinian algebra is algebra which, more generally, which doesn't have decreasing chain of ideals, and clearly, in that case, every chain of ideals, decreasing or increasing, terminates, stabilizes, because it's finite-dimensional. So every decreasing chain of ideals stabilizes. Then you have a smallest ideal which doesn't have any non-zero submoduli. Let I be minimal non-zero ideal. It is a subalgebra in the sense that since it's ideal, you can multiply elements of it. I inside A is subalgebra. And I'm going to prove that I contains idempotent. In fact, I contains unit in it, which will be idempotent because unit is idempotent. Okay, this is step one. Step two, which is pretty obvious, that for each x inside I, which is non-zero, x non-zero, xi is I. Well, it could be zero, in fact. But at some point, I will assume we have no nilpotence, so yeah. So, okay. So let me do the should put here no nilpotence. I think otherwise this proof just stupidly fail. Sorry. Anyway, I'll assume it has no nilpotence because we will apply it only to the case where we have no nilpotence. And okay, so we have this. Xi is equal to x. Otherwise, it will be a smaller subset, or xi it will be 0. But yeah, so Sorry, here, well, I already assume it has no nilpotence. And here it's not assumed. It's just my error, sorry. Anyway, so if xi is equal to I, because x squared is non-zero. Because x squared is non-zero. Okay, step 3. We will find a linear relation between find linear relation between x squared. Is it x here or z? Okay, sorry, it's z, so let's call it z. Z here, z squared, and I find linear relation between the powers of z. It exists because it's fine dimensional. Exists because I finely dimensional. So we think of these guys as endomorphisms, endomorphism of I. Now, z is invertible. So we can always, if you have p of z equals 0, and the free term is 0, you can just divide it by z. After you do that several times, you obtain a relation where free term exists, non-zero free term. And this gives you a nice relation, identity of I is equal to some polynomial of z. So it's equal to a z plus bz squared plus and so on, where a, b are elements in K. This is a relation in endomorphism, in endomorphisms of I. Okay, but now we realize that for each non-zero element, z acts invertibly on I. This means that, so step 4, I is embedded into endomorphisms of I. So every relation which you can have in endomorphisms holds true in I. And then we shall write this guy, then AC plus BZ squared plus and so on. This belongs to endomorphisms of I, satisfies, so let's call it X, or it is called here U. Okay, it's called U here. Let's call it U. U satisfies Ux is equal to U, to X, for each X in I. And then, okay, this brings since this is multiplicative embedding, then U is idempotent. Idempotent, satisfying Ux is equal X for each X inside I. Okay, we proved the existence of idempotent. In fact, we proved the existence of unit. Questions, comments? So it was step 5 in this. So it was this step 4 corresponds to step 5 here. So we proved that and if it has no zero divisors, it contains unit. Because if it has no zero divisors, this means that we can just apply this argument to A, which is its own, because every element is invertible. So So corollary, every K algebra without zero divisors is a field. Well, it contains unit. That's all elements are invertible. Well done. Now we can prove this theorem which I raised about existence of direct sum decompositions. So theorem. Let A be semi-simple. Semi-simple means non-nilpotence. Semi-simple Artinian algebra. Then A is direct sum of fields. So it's algebra over K. So this is extensions of K. So obtained essentially for free this direct sum of fields. And the proof is very easy, just based on this observation. So proof. There exists unipotent say A inside this big A. Then A is direct sum. So it's AA plus 1 minus A. They are both non-zero subalgebras. It's direct sum. And they're smaller dimension. So by induction on dimension, we can assume that these both subalgebras are already direct sum of fields. This is done. Questions? Comments? So this is how you decompose every Artinian algebra onto direct sum of fields. Uniqueness. So for uniqueness, you have to realize that there's a certain order on unipotence. Namely, if one unipotent is divisible by another unipotent, you can consider one of them smaller than another. It's like stronger statements in logic. And there are minimal unipotents, which are not like, which don't have any, which are not a product of any smaller unipotents or bigger, well, smaller unipotents. And this is precisely the unipotents which correspond to fields. So this decomposition is just decomposition of unit into a product of irreducible unipotents. This is the idea, but the proof is you can state it without any statement, without any unipotents, well, without any decomposition. So if you have a direct sum of Ki, then this decomposition of Ki fields, this decomposition is unique up to permutation. Questions? So proof. Okay, we have, suppose we have two decompositions. So A has two decomposition, two sets of unipotents, two sets of unipotents. AI and BI. Then you have like a smaller set of unipotents, bigger set of smaller unipotents, which is sum of AI BJ, IJ, all of them is equal to 1 because sum of AI is equal 1, sum of BI is equal 1, This is because this the set of unipotents come from the direct sum decomposition, and you just multiply them. Okay, there could be two things. Either this set of unipotents, AI, BI, is unipotents, AI, BJ, unipotents, are just the earlier set of unipotents. They're the same. We don't gain nothing, but what we gain is that these two are the same decomposition, because unipotents uniquely define your decomposition, just Ki. So we take this unipotence as follows. So Ki is AI times A. This is how unipotents correspond to subfields. Okay, so in one case we will have this. We don't lose nothing, we don't gain nothing. On the other hand, it could be a smaller decomposition, so none of them are equal to AI and BI. In that case, suppose that not all A, we fix A, say A1. So I take A1, just to simplify notations. Not all A1 Bj are equal to A1 or 0. Then you have K1 is equal to direct sum of A1 Bj, K1, right? The same argument. Just you use that sum of Bj is equal to 1 and Bj prime is equal to 0 if j is not equal to j prime. So this gives you a decomposition of this field. That's impossible because it's a field that doesn't have any unipotence. So all of these guys except one are 0. This means that the decomposition defined by Bj is equal to decomposition defined by AI. Otherwise, you just multiply the decomposition and obtain a smaller decomposition, which is impossible. Okay, now I think we can take a break. You have like until 2:30. And we shall continue with application. Then you can take a tensor product, M times over R with R prime. This is R prime model. It's finally generated R prime model. First, why it is R prime model? Because you can multiply. I mean, it contains R prime acts there. So if you have an element of R prime, you'll just act by this element on this tensor product. And it's finally generated because the generators of M, you can just move them to here. If you have x1 dot xn generate M, then x1 times 1 dot xn times 1 generate M times R prime. This is trivial. Now let's define finite maps or integral rings. So definition, suppose you have x to y, a morphism of affine varieties. This gives you a converse morphism y to x, oy to ox, a morphism of rings, corresponding rings of regular functions. What is it, f? It was f. Okay, then this is f star because it is the same map but on functions. Then we consider ox as oy model. I mean, every time you have a homomorphism of rings, the second ring is model of the first. You can multiply. If you have an element here, you can multiply points, I mean, vectors in numbers in OX by images of elements in OY, and this gives you a structure of a model. And F is finite morphism morphism if OX is finally generated model, OY model. And yeah, in that case also OY is called integral extension. Integral extension of OX, right? No, sorry, OX integral extension of OY. So obvious example of integral extension is just finite extension of fields. Let me give you another example. So you can have even polynomials, have T of x square, y square, and xy. You have all polynomials. C of x and y. So this is mapped to that. But then this is generated over that by x and y. And every monomial over over xy is generated by even monomials x and y. Because if you have odd monomial, it's either divisible by x or by y. And if you divide it by x and y, you will obtain even monomial. So odd monomials are even monomials multiplied by x or y. So this is an example of finite map. And if I think we discussed that at some point, that this map has easy geometric interpretation. You have c square, which is mapped to this c square by plus minus 1. So what is c square by plus minus 1? It's polynomial functions which are invariant under plus minus 1. So this is it. This is even polynomial functions. This is all polynomial functions. This is finite morphism. In fact, all finite morphisms are obtained by as group quotients. We shall see that at some point. So this is, well, no, I'm not entirely correct. There's another, let me give you another example. We have a singular curve. Oh, yeah, this is the good example of finite map. You have x, y is equal 0, and then you have a union of two lines. X is equal 0, line, and then you have y is equal 0, another line, in c square. So this, it's disconnected union. Just you have two copies in c square, and you map this into that. I'm not going to tell you now why. It's an exercise for you, but it is really finite maps. It's not not hard to see. Another example is the following. You have a singular curve. In c square, defined by x square is equal y third. It has this kind of singularity. I mean, you can easily see its graph, and you will see that it is singular. But then there is, let's consider a map from C to this curve. C to this curve, which is given by, I mean, if you have a map, yeah, right. If you have a map from C to this curve, this means that you have a map from the corresponding ring. So what is the ring of this curve? It is a ring where you have two generators. Let's call it Z or U and V. And you have U square is equal to v power third. Oh yeah, no, I'm sorry. It's just you have these generators. Anyway, you have C of t. So we are interested in map from C to this curve. This means that you map from this to C, and you have x goes to t third, and you have y goes to t square. And then t square power third is equal to t third power square. So this is a good morphism. This is a morphism of algebraic varieties, which is clearly polynomial. Just you have this singular curve, and you have smooth curve, just a line which is mapped to this curve. And then it's also finite because everything is generated by t. The ring of polynomial functions is generated by t squared to t third and t as a model over the ring generated by t squared and t third. So this is examples of finite maps. We shall work with it a lot, especially with this kind of maps, because it's a desingularization. I mean, the singular curve, you obtain something which is not singular, but this is an important case where you can desingularize variety by doing something which is generally one-to-one, except that it is in that singular point, it's not one. It's one-to-one in points, but it's not one-to-one on functions. Outside of it, it's holomorphic functions goes to the same holomorphic functions, just one-to-one, like by holomorphic map. Okay. All right. Now I will give you another, well, it's not characterization of finite maps, but it's almost a characterization. It at least explains the term that they're called finite. It's a theorem. If you have f from x to y is finite, then each point y, small inside y big, has non-empty finite set of preimages. Proof. Okay, we need to prove that f minus 1 of y small is finite. But then what is, we already proved what is f minus 1 of y. If you have the corresponding ring was described, so it's or the spectrum f minus 1 of y is spectrum of a spectrum means it's a set of maximal ideals in the or prime ideals if you are interested in, but let's do with maximal ideals of the ring. Now we take O, so this is the bigger ring of X, and multiply it over O of Y by O of Y quotient by My. This is something we have already done. Okay, so this is actually complex numbers because it's maximal ideal in algebraic variety. We know that the quotient ring by the maximal ideal it's Hilbert Nullstellensatz. Now, this is finally generated model over this ring by this lemma which I erased just. So this is ring is finite ring, no nilpotence. Well, you can check, but it's finitely generated. Well, you can always take a quotient by nil radical if you are interested. Finitely generated and finite dimensional space, vector space over C. Because this finitely generated model over OY, then you take a direct quotient that becomes finitely generated over this quotient ring, which is C. Okay. No, we don't, because we just proved that every finitely generated without nilpotent with algebra without nilpotents is the direct sum of fields. In our case, it's the fields are C. Then they're finitely many, they are non-empty. So the set of maximal ideals is this ring is finite, and we're done. Finite and obviously non-empty because it's non-empty ring. In fact, the stronger theorem is true. I'm not going to prove it now, but maybe at some point. It's a commutative algebra theorem. It's called Cohen somebody. Do you remember? Nobody? Well, sometimes it's just called theorem of lifting and of ideals. Anyway, so this is the following theorem. You have A containing B integral extension. Then you can take a chain of prime ideals. P1 containing non-equal to P2, containing non-equal to P3, and so on. Pn, everything inside B. Then there exist and finitely many. So it exists, and there are finitely many of them. Finitely many prime ideals. Q1 subset not equal to Q2, subset not equal, and so on, subset not equal to Qn. Inside B, A, such that Pi is obtained as Qi intersected with B. Well, the opposite is obvious. It's really going up. You can go up, but the going down is trivial in that context. How you can interpret it? Well, you can think of for instance, Pi is subvarieties, and Qi is subvarieties. And this means that if you have a chain of subvarieties, which are distinct, this chain is lifted to chain of subvarieties so from Y to X. And this gives nice things. For instance, you always, up to some normalization, you always have finite morphisms to Cn. Up to some shifting and cheating, you can always have a finite morphism from your X to Cn. But then in Cn, you can, for instance, have a chain of subvarieties, which is equal to like codant subvarieties, which is equal to a dimension. You can lift it, and this would give you a family of subvarieties, increasing dimension, all of them irreducible. And then you can define dimension as maximal length of chain of subvarieties. There's lots of such things. They mostly belong to commutative algebra. There's almost no geometry. So I would, unless I would really need it, I won't give it to you. But you can find it in IT McDonald, and you really should because it's important. OK. I think we're done with this geometry. Let's go back to algebra. We don't have much time. So I'm going to well, what I was going to do in the end was to prove a primitive element theorem, stating that every finite extension has a primitive element. This is false, unfortunately, in characteristic P. This is true for what is called separable extensions. And the whole business with separability is unpleasant. And I'm avoiding it by giving a strange definition of separability, which is, if you master Galois theory, you would see that it is equivalent to the standard definition of separability if you know the standard definition of separable extensions. If you don't know, then you don't care. And So this is true in Critério 0 and for separable extensions, the primitive element theory. This is the first observation. And okay, but before I do that, I would have to do lots of tensor multiplication of fields, because this is in fact just one of the approaches to Galois theory. And now I want to ask you, I can spend 2 lectures or 3 maybe on Galois, just give you all Galois theory in this language if you demand it. If you don't, I would just go to algebraic geometry and avoid field extensions. So what is your preference? Do you want me to give you Galois theory or not? Who wants me to give you Galois theory? Please raise a hand. Who wants me to not to give you Galois theory and go to algebraic geometry, avoiding Galois? Okay, you want me to avoid Galois. You will. So I don't think I need from Galois theory anything except for this primitive element. So I'm not sure I would be able to finish it today, but at least I will give you most of it. Okay, now bilinear invariant forms. There is something if you know cohomology, you always have it because it's Poincaré pairing. If you don't know cohomology, then just I would give a couple of examples, but really you have lots of them. So definition, an invariant. So suppose you have A is K algebra. An invariant bilinear form is G from A times A to K, which is bilinear, K bilinear, and satisfies G of A, B times C is equal to G of A, B, C. If you are lucky to have unit, then it's even easier because it's always defined, uniquely defined by a linear form, remark. If A contains unity, then you have a form, epsilon, from A to K, which is equal, epsilon of A is equal to G of A1, or 1A. I assume it's symmetric. Sometimes it's not symmetric, but for all our application, it is symmetric. So it's symmetric. Okay, if it has unity, then G of AB is equal to epsilon of AB, right? I mean, you just move, oops, sorry, A. Yeah, because it's the same as G of AB1. So if you have unity, then you have this, it's the same as just a linear form. So that's an example which makes sense if you know cohomology, and otherwise it's just a silly example. But it's an example, well, it's an example. So you have algebra A, which is equal to C of xy, quotient by x power n plus 1 and y power n plus 1. So I take a quotient by the ideal generated by these two guys. In fact, it's the same as C of x, quotient by x power n plus 1, tensor product with C of y, quotient by y n plus 1. This is the fine dimensional algebra. Most of the elements are nilpotent. X is nilpotent, y nilpotent, and the products are nilpotent. And then you have the following form, epsilon of, you have a sum of x, a, I, j x power I, y power j, where I is and j are less than or equal than n or bigger or equal to n0. And this is equal to a n n. You take a projection to the biggest degree term, which is non-zero. And then this is non-degenerate. Well, the corresponding two form is non-degenerate. You can just easily express it. In fact, G of such a sum aij xi yj, and then you take some bij xi bj. This will be equal to sum I plus L equal n, j plus k equal n, and then you take aij b lk. Right? This is easy. And this is obviously non-degenerate form. It just takes, it has this matrix. You have, well, you can write its matrix. It has just diagonal terms, but like off diagonal. Anyway. Yeah, so for fields, every form is non-degenerate or zero. So remark. Or claim. If you have C k big over k small is a field extension, and G invariant, bilinear, then G is equal to 0 or G is non-degenerate. Proof. Okay, so suppose epsilon, this has units, so G is determined by epsilon. G of xy is equal to epsilon of xy. Something we have already done, right? Now we have a G of a, suppose the epsilon is non-zero, epsilon of a is non-zero. Then G of x minus 1a is non-zero. So for each x, there exists another element such that their pairing is non-zero. It's a non-degenerate form. So the most important bilinear invariant form is trace form. It's really like the most important form in number theory. If you do number theory or Goulart theory, you encounter that every single moment. Well, who knows definition of trace in linear algebra? Please raise a hand. Almost everybody. Good, good. This is the definition of trace. You just sum diagonal terms. The important thing that it is independent on the basis, which you, of course, can prove. For instance, it's the term with x in the characteristic polynomial. Or there are some other arguments showing that trace is, or derivative of characteristic polynomial evaluated as 0. There are other arguments proving that trace is well defined. And now we can, if you have Artinian algebra, every element can be interpreted as an endomorphism. So definition, let A Artinian algebra over a K. then you have x and y inside A. Trace of x, y is equal to trace of the multiplication operator of L x y, where L x y applied to z is equal to x y z, and L x y is endomorphism of A. A is fine dimensional, so this makes sense over, fine dimensional space, you have a fine dimensional endomorphism of fine dimensional space, it has a trace. This is the definition of a trace. Yeah, and of course it's not degenerate unless, if K over small k is a field extension, then trace, well, clearly trace is invariant. It depends only on the product. Trace is non-zero unless, and trace, extension and trace is non-zero, then trace is non-degenerate. So it's either identically zero or non-degenerate, one of two things. I'm almost out of time, so let me show you the final slide for today. This is about separable extensions. This is something which makes it troublesome if you do Galois theory in characteristic P. In characteristic 0, it never happens. Namely, the trace is never, in characteristic P, trace is never identically 0. In zero characteristic. In P characteristic, it can be identically 0 or not. So definition, field extension, K over small k is called separable, if trace is non-zero. So remark, if characteristic of k is zero, is non-p, zero, then k over k is separable, always separable, because trace of identity, or just unit, is dimension of k over small k. And this is never 0 because it's positive real number, positive integer number. Of course, it can be 0. Okay, let me give you an example of non-separable extension, and I am done. I think I'm improvising because we're still out of time, so there is nothing to do, but at least we shall have something. So we have a field fp, finite field, and then we add t. This is rational functions, quotient of two polynomials over finite field. Then you have a polynomial p of t, t we have already, so p of z is equal to z power p minus t. I claim that fp of t, quotient by this polynomial, is non-separable. I don't have time to do that. It's an exercise for you. Sorry. But we're done for today. If you have any questions, please ask. Thank you very much.